half of it, the example.
Okay.
I think I got the chance.
All right. Let's go to. Oh shit, where were we? Chapter 6.
Yeah.
6.3.
Yep.
Root finding.
Okay. No, non-linear equations.
Okay. Okay, folks. Any questions before we get started today? Okay.
How do I control the screen?
Yeah. Do you know how to go up and down?
No.
It's going to be opposite of what we expect.
Okay.
All right.
All right. Ready? So we've been talking about linear equations so far in chapter 6 and how to find the solutions for them. This chapter focuses on nonlinear equations. So, for example, 2 minus e to the negative x is a nonlinear equation, meaning like it's not like a straight line. So the way that the book solves this is by something called the relaxation method. So it pretty much just puts values into x until it reaches like a relaxation or like a number that's kind of the same overall.
Let's pause for a second. Have we ever seen this technique before? Yeah. Where? Right? And before we did over relaxation, we did relaxation. So when did we use this? You ever done that? You ever seen that before in your whole life? You ever seen this before in your whole life? No, really. Okay, what was this?
What is called single, I think is a possible, it's not the.
Yes, this is the Poisson equation or the PHYS equation. And in this example, we had two boxes, negative and positive charge. In this one, we have V equals V naught, and everyone else V equals 0, right? You remember these problems? You all remember these problems. You all did them, right? Go ahead.
Okay. So that works for some, but there are some equations that don't really relax as well. For example, oh, I actually skipped a part. What was it? Oh, I know, I'm good. Yeah. So for this one, it doesn't really relax as fast or as good. As you could see, it's 2.1, 0, 2.7, 0, 2.7, 0. So when they couldn't do that, they did a trick to get it within this form by taking the log of the equation. And by using this formula instead of this one, they used the same relaxation method and came out better. Next. This is the rate at which it relaxes. Didn't really understand the math too much, but yeah, I don't know. Do you?
That's okay. I mean, the rate at which it relaxes is mathematical. You don't worry about that too much.
Okay.
The technique is what matters here. So you can even switch 3.2.5 6.3.2, you can skip that one.
Okay. And then it talks a bit about the error of the relaxation, which we could find with this equation right here and all these derivatives and stuff which come from other equations in this chapter. But yeah, then it just goes into the example. That's pretty much the whole chapter.
There's more to the chapter.
There's more? Oh, that's all I read.
A lot more.
Oh, yeah.
Okay, that's as far as you got?
Yeah,
Okay, all
I
right,
can see that.
no worries. Okay, let's keep going then. You can sit down. Okay, so after realizing that we can do relaxation in this example here, what we're doing essentially is we're saying, let's make a guess for the left-hand side. Let's make a guess for the right-hand side. And what we're going to do is, because they're supposed to be equal to each other, one of them will direct us towards the right answer. Okay? So what I mean by that is here you have some, hold on, let's go back here. You have x equals something, right? 1 minus log x. Well, of course, this one here is going to converge at a little bit of a an issue, right? So for example, here it vacillates, it jumps back and forth around this point, and it goes towards the correct solution of 1. Whereas this one here, when we write it as x equals 1 minus x squared, it jumps back and forth between 0 and 2, and 0 and 3, and 0 and 3, back and forth, and never gets close to the solution, right? So what we're asking this not relaxation to do is the same thing that we asked over here. Okay, when we did relaxation before, we said that the nearby information, right, whatever the slope is going to tell us what's happening at that location. So rho was where the charges were, and that's going to set up the slope nearby. And similarly, we're going to use this in order to start with a guess and then use the rest of the equation to tell us where we're going. Okay. So similarly, we have some relaxation method here. And what we can say is, let's take some function. Okay. Let's look at the derivative, which direction it's heading at that location, and use that information to head towards the 0 point. Okay. So the example that we have here is something from ferromagnetism. So what that means is that M is a magnetic moment. There's some properties in here like the magnetization of the metal, blah, blah, blah. That stuff doesn't really matter. What really matters here is I have M on one side. You can think of that as X, and then something inside of the hyperbolic tangent. Now, hyperbolic tangent, I'm going to guess most of you don't have an intuitive sense for, right? That is a combination of exponentials, e to the x plus e to the minus x, stuff like that, right? So this is necessarily going to be a nonlinear equation. And we say to ourselves, okay, how do I find m such that this is true? So if I put in 1 for m, and then I put in the tangent, hyperbolic tangent of this value in here, I'm going to get two numbers. They're not going to be equal to each other, right? Okay. But instead, what I can do is I go in here, I say, listen, I want this to be accurate to within 1 to the minus 6, right? I set up a list, and I don't know how long it's going to take to converge. And I'm just going to do a series of guesses. And each time I'm going to use the equation to make a better guess, right? Okay. So the first thing I do is I guess m equals 1. And I set a really big error. Okay. And then I'm just going to keep guessing until I get closer. So the first one I do is I say m1, that's going to be 1. That's going to now be equal to whatever the result is of that. And my old guess for 1 is now going to be what m2 is. I'm going to keep switching.
And what I'm looking for there is I'm just looking for the right-hand side to tell me about the left-hand side, right? You're basically playing a guessing game. And the important thing is here is that the error, kind of like what we were talking about earlier, you have to use this derivative. You can find that just in the textbook, the section that we were looking at. As long as you can take a derivative of it, it's quite straightforward. And this tells you how close you can get, right? And then you can do that for any amount of t. You can do this over and over and over, and it's always just going to give you M1 whenever you're done. Okay. So that's not the only way to do it. We saw, of course, that on one side we had X. So this side we have some values of X. So there's some other ways of doing it. So of course we have over relaxation. We saw that before. We can kind of speed up the process. So instead of just saying, take it equal to X, take it equal to X times a small amount. So jump faster in that direction. You can also do this with more than one variable. Oops, where'd it go? Yeah, more than one variable. But more importantly, you can do what's called a binary search. And we've kind of seen this before. We saw this with respect to the shooting method. You guess above, you guess below. You guess above, you guess below. And what happens is after every guess, you take the output of your guess and you compare it to your answer. Now imagine you have some function, f of x, and you want to find out where it goes to 0. On one side, the derivative will be positive, right? Or sorry, on one side, the values will be positive, and on the other side, the values will be negative. That's the definition of going through 0. So there, you just have to check a sign. And remember our example before. We had something equals x, right? Well, if I take that something equals x and I put it on the other side so that it's everything equals 0, that's an equivalent statement, right? So I can do a binary search on that thing, right? Rather than the relaxation method. So I can take this method and I can just take this function. Let's say it's the tangent, just subtract x from it. That's going to be my new user-defined function. And all I have to do is ask, am I positive or negative? If I'm negative, right? If I'm negative, move to the left. If I'm positive, move to the right. Or vice versa. If it's flipped the other way around, you want to get closer. Okay? And there's a wonderful little algorithm here. Pretty straightforward. You're going to take the average of your guesses. You're going to pick in between. Sometimes that's called the secant method or the bisection method, because what you do is you pick in between the two, and then you pick in between the two of those. So if, for example, here's our 2, I pick and I compare to this one, and this is negative, then I pick halfway in between this one, and then I pick halfway in between this one, and by that point, I'm getting quite close to the root. We call them the root. They're the zeros. You familiar with that term? The root of an equation is 0. Okay, so that's one technique. We're going to use that. That's really fun. You can use that for Wien's displacement law. You can derive the displacement law. And then you have Newton's method. And Newton's method is quite similar to Euler's method. What we're doing here is we're taking advantage of the derivative. The derivative tells us which direction to go, right? So for example, here is some point x and some distance, okay? Let's take this point here. There is the derivative, right? So this is heading towards my root, right? Because what I'm trying to do is I'm trying to go from x prime, new location, is x minus delta x, x minus delta x. Well, that's just x minus the function divided by the derivative, right? Because this delta x here is this thing divided by that, right? By definition. Does that make sense? Okay. So what that means is that this will be a much faster way to get there. Because if the slope is like this, kind of slope like that, then instead of taking just one tiny step at a time, or going back and forth and back and forth and back and forth, this thing will start us in a direction and it'll follow the curvature of the function itself right down towards 0. There's another technique that we won't actually get into today, but it's, all of these problems are essentially solving the same thing. And it's how do you get from the top to the bottom? Okay, so you can imagine, if you will, that this is a 2D surface or a 3D surface. Okay. How do you get from the top to the bottom the quickest? Falling straight down, yeah. As close as you can get to straight down. So if you're thinking about skiing or snowboarding, you take the black diamond, right? Those go straight down. And these are called maximum descent models for finding the roots, right? So what they do is they use the actual curvature of the function itself, and they go as fast down as they can, right? And these are all techniques for finding the roots, okay? You can really, if you'd like, you can get into the details here. This is going to tell you about the approximation error, things like that. But really, I would quite recommend that we start with something like this. So you have maybe, here is an example of the hyperbolic tangent from that previous problem. We can use Newton's method here. So this is going to be our new guess, x prime is equal to our original guess minus the ratio of the function divided by the derivative, right? So the function was tan x minus u, and it's going to be divided by the derivative, which is just cosh squared u, or cosh squared x, sorry. Okay? Okay, so then we start with some initial guess. We can go through here. By the way, you may need a, they call it arctangh H. This is, this is not the arctan function. This is for finding the roots of the arctan function, right? So that's what they're doing in here. So be careful, right? This is not like what you would use to find arctan. Okay. And they're doing the same thing here. They set delta equal to 1 for some given u. And then they find the absolute value between delta, which is going to be the difference between these two, and where you're headed. You head in that direction, right? You may be worried. You're like, well, why is it only minus? Well, delta can, of course, be negative, and subtracting a negative is a positive, right? So as long as, I mean, in that example that we showed here, we're heading back towards the root. But if I go over here, right, then the ratio of the function divided by the derivative, so the derivative is positive, but the function is negative. So now I'm heading to the right. And you'll notice in any time that we see that, so let's take this part here. Let's say we're jumping here and we want to go to the left. Okay. So the function is positive and the derivative is positive. I'm heading toward the left. What about the place that they call x here? The function is positive, but the derivative is, it's actually negative because it's sloped down. See where I have my thing? Sloped down. So now we also head to the left, right? So this is good too, because let's say I start over here. The Newton method is going to be able to jump right over this little hump, and then all the way back down. Okay? Questions, comments, concerns? Okay. This is the most fullest class we've had. 2, 4, 6, 8, 10, 11. It's almost everyone who's enrolled in the class. He's online. Okay, so let's do a lot of fun things today. We are going to do bisection. We're going to do root finding. They're going to feel dumb. Okay? They're going to feel like, this isn't helpful. But really, this is sort of that basis to the techniques that we were talking about earlier, right? So not only over relaxation, but any sort of algebraic problem we might want to know a computational answer to, now we can find, right? You could put any equation in there and we can solve it non-linearly with the computer. So now you'll have every single tool to do computer, right? Computer is you. Okay? Or like, what does Trump say? Everything in here, all computer. Something like that. Okay. What? Clip it. Yeah. Don't worry, it's only recorded for everyone. So you'll see that there's all these different types of problems that we can end up doing. The secant method is here. What we'll do then is we'll take some substitution for the derivative as opposed to the derivative itself. Remember that the derivative is great if you can take it, sometimes not so good to take, right? Sometimes the function not well defined. So maybe what you want to be taking maybe you don't have a functional form. You can take something like the derivative at a certain location is equal to the function at the location and finite difference near the equation, right? That is by definition what the derivative is supposed to approximate. And you can do it for more than one variables. You can do it in order to understand resistances. You can do it to understand the Lagrange point, which would be the places in which gravity is balanced around a planet. And then we'll get into maximum minima in the next time. And this is how you do things like the golden ratio search. Have you ever seen that? It's cute. Okay. Where are we? Okay. So Elliot will present maximum minima on Wednesday. Today is Monday, right? Okay. All right. So what do we want to do today? So we've done 6.1 and 6.4, right? And this weekend we're going to do, or this week we're going to do, we did this 9.5, 9.6.3, and 6.5. We did that over the weekend. Raise your hand if you finished the homework this weekend. Raise your hand if you started the homework this weekend. Okay, raise your hand if you intend to pass this class. Okay, raise your hand if you're going to pass this class. Okay, interesting. All right. Yeah, you got to do the homework. There's no time. There's no time to mess around. Other classes, you're like, oh, they're more important. You can fail this class and then you can take it again next year. I mean, that's perfectly fine with me. What do you want to say about that, Emmanuel? He doesn't love it, right? But maybe you get it more the second time. It just seems like maybe it's not a good use of your time, especially since it's 16 weeks, right? So I would deeply recommend, because you will have to do the following 3 things. You have to finish all of the homework. You'll have to do your final project, which is not even written on the board. So you have to do it. And then you have to present it. So you have to make a presentation. So Will was asking me a little bit earlier. He was saying, when do we have our homework submitted? So you have to have all of your homework submitted by 5/1. Everything else after that, I mean, I'll still accept it, but I'll scream at you. Not scream at you, but I'll look at you disapprovingly. And that's worse, right? Okay. You say that's kind of worse? You have a question, go.
So when it comes to our final project, do you want us to make a presentation? Like, can we only be on code couch, or do you want us to do like a whole PowerPoint?
No, it's a whole PowerPoint. So you may or may not have read earlier at the beginning of the class, or maybe even the syllabus, it says one of the skills that I want you to walk away with is scientific literacy and communication. So you're supposed to get up here and present to your colleagues so you can practice presenting. Now, you may say to yourself, listen, I don't like presenting. I don't really want to do it. Okay, that's fine. That's very different than I have a condition that stops me from presenting, right? Okay. If you don't like doing something, it's really not an excuse. For the rest of your life, you're going to have to defend what you did. This is one of the lowest stakes environment that we could possibly have, right? Like, I bring candy, pretty kind. I rarely yell at you, right? Okay. Rarely. I don't know if I've ever yelled at you, right? Maybe just I say things in a condescending way and that hurts more. Hold on. Hold on. Yeah, I cut you to the bone, but that's not what it means to do. The thing about the way that the world works, right, is that you will need to be able to present what you did, and it'll be highly technical and highly sophisticated work. No one will ever just take what you did for, oh, I just did it. Maybe when you work in a low stakes job, that's perfectly fine. But if you're going to work in science, you need to be able to defend what you did and explain it easily, right? So we practice it, because you don't get to this without decades, not one, decades of practicing speaking in front of people. So I understand that it's overwhelming and everything else. It's the lowest stakes possible. Maybe we'll get pizza or something to like take everyone's edge off. Okay. Reasonable? Okay. 3 questions. 1, 2, 3.
I'm just like wondering, like, is there a way to put our code couch stuff onto a PowerPoint? Like,
No.
or-
I don't want to see code.
Oh, you don't want to see.
Did you read? You didn't read the final? Oh, yeah. Okay. So here's the thing that we're going to say. Another thing I'm going to say. Read. Read, read, read. You know what makes your generation different than my generation? Y'all motherfuckers hate reading. I don't get it. You're like, oh, I fucking hate reading. It's like you learned how to read really young, and then you're like, that's stupid. Give me some TikTok. Okay. I don't know how to put my syllabus on TikTok. I mean, I probably should. That would be great for the fall, but I'm not gonna do it. Go ahead. It says in the material, yeah. That's correct. So if you haven't read it, reread it. Yeah. Didn't you have a question? Okay. You want candy? No, you didn't. Well, you get candy when you present. Didn't you get a candy when you presented? All right, I'll get you a candy. You didn't get a candy? That's a lie. All right. Well, I brought one candy for one presenter, so I'll go get 2 more. Let's pick what problems we want to do today. So you need to do this, and you're going to get more linear. Yeah, sorry. Pair programming is due the day that you do it. Yeah, so all the pair programmings are due the day of. You see? So this is 3/24, and it's supposed to be due tomorrow. This is 3/26, it's supposed to be due tomorrow. But it sucks. I prefer that they get done, right? They should ideally get done. If they don't get done in class, that sucks, right? If you do them, great. They should get done in class, right? That's why we have like catch-up days, and that's why we have office hours, right? How many hours do you spend outside of class working on this? Raise your fingers. Okay, that's the right number. Oh, shoot. Yeah. Yeah. If your number is this or this or this, there's a reason why you're not doing well, right? It's 6 hours of classwork outside of this class. It's rough. Especially when it's like, I gotta do it. Well, not me. So I have an idea for how to do this next semester. Every semester I learn something new. And next semester for fall, I'm gonna give you guys timesheets. Anyone taking math methods? Anyone taking observational astro? All right, you're gonna get timesheets. And you're gonna have to fill out a weekly timesheet to show me what you did.
The reading log.
What's a reading log?
The monitor requires a transcript. Yeah, like they did that in.
Apparently, I should never have brought it out of style. Because it used to be, I mean, for some folks, it varies, right? Some people are like super on top of it, some people are not. And then you just never know, right? So. No, no, no. I mean, you can lie, right? I'll know. It's just for you, right? It's your education. It's your money. So, you know, you want to spend the units again, that's fine. Okay, so the idea of grade and the idea of learning should be different. If you learn good, you should get good grade. That is my number one thesis. Okay. In order to learn good, you need to do everything in the class. You need to do all the homeworks. You need to do the project. You need to do the presentations, right? I didn't put them in because I was bored. I put them in because they serve a purpose. If all of them get completed, your grade is good, right? That's my philosophy. Right, because each one is a communication, right? So if you get up and you do your presentation and you're like, yeah, I did this and 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 I did this. And I say, why did you do that? And you go, I don't know. Right? Anyone can recite anything. Anyone can copy and paste anything. Everything is a communication. Can you demonstrate your understanding? Homework is intended to demonstrate that you got it. Right? Because you might have mastery, but you might not be able to show me. And vice versa, You might not have mastery, but you might be able to recite someone who did have mastery, right? I have to see both of those. Grading is very, very finicky, right? Because I have to somehow go inside your brain, pull out the information, lick it, see if it's right, and then put it back, right? You know how people like check the quality of gold by biting it? I don't know. Can't do that with brains. We're not supposed to anymore. Okay, so let's have a look here at which ones we want to do. One of my favorites is so you already did this one, right? For relaxation for 2D. Let's do 610 for sure. I think that's the easiest one to start with. And then I don't want to do 613 unless that's a homework problem. It is a homework problem. Okay, let's do 610 for sure. Maybe 611. We'll see how far we get. C'est bon? Okay, so find a friend. If you are left without a friend at the end, I think Elliot would love to be friends with you. Whoa, 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 not three. Double doubles. Everyone's got a pair. Oh, but they just said they were friends. Yeah, has anyone not worked with someone so far?